Hello everyone, welcome to my control systems final project, a solar powered well pump system. Project purpose and how did this idea come about? We're going to develop a control system with a feedback mechanism to show proper working of a physical control system, build the Bode plot and root locus to show stability and or instability of the system by changing its gain. This idea originally came from needing to water a garden about 100 to 150 away from a cistern in a remote area and needing an automatic timer. For this class, I actually added the relays and everything else like that to have negative feedback. Solar power and battery pumps are nothing new. The solution was developed as 24 volt DC for pump for safety reasons and also to decrease the amperage draw on the batteries, keep the heat down and the draw of the power. For pump safety, a negative feedback is integrated to whereas if there's no well water in the cistern or if the well is dry, even though the PLC is calling for power, the pump will not be allowed to run. Optionally, which I have also added, is a tank overfill negative feedback. That means when the secondary tank is full, excuse me, that there will be no more water allowed. It'll break open the circuit once again and the pump will not be allowed to run. So the basic drawing of the system, you have your sunlight coming into your two 12 volt polycrystalline series wired panels into a 10 amp charge controller, which are going down to the batteries. And then you've got a 10 amp fuse protection, and from there it goes into the PLC. Now, once the PLC wants to send out power to the pump, if there is not enough water in here, it breaks open the circuit, and if the tank is full, it breaks open this circuit. So you can use it as a sprinkler or as a tank fill. I use it as a sprinkler, which was actually highly effective. There's 30 feet of lift in this pump, 15 gallons a minute, 260 watts, about 85-90% efficient, and the load is somewhere in the neighborhood of less than 10 amps constant. The schematic of the system, you can see that I've developed two solar cells with a 12 volt series into a charge controller with its battery level. Then you have into your fuse protected battery bank, and then from here we send power to our timer PLC. Now when the timer wants to close this relay, the first thing it's going to do is send a power to both float fly switches, and if they remain open, then they will not kick open this relay, which is for the well supply, saying yep, there's water in the well, and then it'll pass through and say, is the tank full? Nope. Okay, well, we'll go ahead and kick the submersible pump motor on then. And that's how the basic system works. Block diagram, the transfer function, we have our solar power coming in, then comes into our PID, we have wall supply feedback H1, tank empty H2, and this is just a base signal to track for the Bode plot. Now if we look at our time domain function for a PID into the Laplace, our new formula becomes C equals S squared plus S plus 1 over S, but recognizing G of S is C over 2 plus CH of S, H2 of S, our final result is S third plus S squared plus S over S third plus 3 S squared plus S. Now our root locus and Bode plot, the system is always stable no matter what unless you lose voltage to the PLC, and I suppose if you were to really wrench the volts up to your pump you could potentially burn it out. But the system was highly stable really no matter what, so I decided to add a negative K value in there to have some fun with it. But even as you can see, we add a negative 2.7 value to K. It takes just over 800 seconds, which is somewhere in the neighborhood of 5.5 minutes, I think. Or maybe it's 10 minutes, whatever it is, 15 minutes. Anyway, at that point, it finally starts to become unstable. Here's a little video to show you how it works. And one thing I didn't mention in this project is that those two relays are normally closed, not normally open. And I did that for conservation of power. I don't want two relays constantly drawing power, even no matter how minute it is, because in a remote area, conservation of power and battery is key. This is the MATLAB simulation.
Here's a brief simulation of my MATLAB setup that I have for my solar pump system. As you can see, there's water properties. I have adjusted them to be at 7.5 degrees Celsius, which is 45.5 Fahrenheit, average water temperature right here. I wanted to get as real as possible, as close as possible. Take one of your well or your cistern, and it has a volume feedback, which comes here to this port here. As you can see, there is currently 13.58 cubic meters, which is about 3,000 gallons. That's a typical cistern. So then from that point, I traverse through this submersible pump up to a pipe that has a resistive setting to make it more realistic at 5/8 diameter, which is what I'm using. 10-meter drain, raising it to a pressure into a Newton to its volume, which is here. So if I change this 30 seconds on a 15-gallon system, it should run about 0.03, which is roughly 7.5 gallons. And if I run it the whole 1 minute, 15 gallons per minute pump, what we're seeing is 0.0608 cubic meters, and compared to the 0.068, which makes 15, that gives an 89.4% efficiency. That's pretty close, getting close to 85 to 95% efficiency. So if we go to our submersible pump settings, we can see there's controls here, normally it's voltage. But you can see the relay 1, relay 2, the volume passes through.
And another thing I did in here is I actually had the atmospheric pressure set to 14.7 psi, and then I went with a standard groundwater temperature, 45.5 degrees Fahrenheit, to try to be as real as possible. Any questions?